What I want to start with right away is to give you a sense of what it is to write socket programs and why it's important. So if you remember, the way we discussed how an application is written is that we have some kind of application over here, and then we have the other end of the application over here. This is a networked application, and between the two we have what what I've been calling the pipe. And this pipe has over here the API, the application programmer interface over here, and there's the API over there. And we actually have two kinds of applications. The client are two ends of a communicator. I'll just talk about that in a minute, called client and server. So we saw an example of a client-server application as a secure shell or NFS, and so you have some sense of what these client and servers are. What we're going to go to in quite a bit of detail today is this API over here. We'll understand exactly what's in that API, and also by the end of the class today, you should know enough to be able to write your own networked application in C. And if you don't want to use C, you could write it in Java or Python or Perl or whatever you want. But I'm going to cover it in C for two good reasons. One is that the C API is sort of the first one that came out, and it has a lot of details, and these details are important, and these are kind of glossed over and hidden by the Java and other APIs, so I don't want to hide them. I want to show you what's actually going on. And the second thing is that the C API is sort of the most widely used. It's most networking code ends up being written in C at the bottom layer anyway, and so it's good to see what's there. So Java is close to C. The syntax is almost the same. For the portion of C I'm using, the syntax is more or less the same. So if you know Java, you'll understand what I'm doing. And then and Python is basically the same as well. Okay, I'm going to first give you an overview. So this is sort of where that fits in. What we're going to focus in is really on this interface over here. All right, so put those sheets aside for a moment because there's a bit more detail. I'm going to first tell you how to understand what's going on, before you actually read through it. So imagine that, actually it's not imagination, with all this lousy weather that we've been having, I was thinking of going on a trip, to some warmer place, to the beach. But on a professor's salary, you can't quite do that. You have to make a lot more money. You have to work for RIM or something. Or rather, you should work for RIM in the old days, not now. And right now, you should work for Facebook, I guess. But anyway, so I thought, how to make some extra money, and I realized I have excellent drawing skills, as you can see. I can actually draw quite well. I have remarkably good drawing skills, and I actually have an office in Davis Center, which is not completely used up with books and papers and so on. I have a little bit of space, so I thought maybe I'd open a tattoo parlor, and make some money, because with my drawing skills and my fine use of pigment and line, I can actually make some extra money, and maybe I can take my family on a trip to the beach. So what do I need to do in order to do that? Besides violating all sorts of rules about opening businesses on campus, which we'll set aside for the moment. Presumably, I need to tell people this business exists, otherwise it's not going to work, right? So what I need to do is to sort of set up a signboard like this. So this is my office. This is Davis Center, I guess. Sort of looks like that, and I'll need a separate entrance because I don't want everybody to use the same. So I'll put a staircase outside Davis Center, and that's my window over there. Make that into a door, and I'll put a sign over here, Professor Keshav's Tattoo Parlor. Tattoos, okay. So there, we have that set up, and so I have a name, I have a door, and then what I'm going to do is I'm going to listen for some customer to come so I can make some money. So here is a person, my beautiful drawing skills at work, and they come up and they basically knock on the door. And when they knock on the door, I'm going to let them in. At this point, I can, do the tattoo, charge the money, and off they go. And then I shut the door, and the next person comes in, and so on, right? Notice that the relationship between the two is asymmetric, right? This person doesn't need a sign on the door saying, I want a tattoo, right? They just kind of see the sign that says tattoo parlor and they go there, right? So I have to put up the side and this person doesn't. So there's an asymmetric relationship over here, and okay, so this side over here, the person who's setting up this kind of service, okay, this is the tattoo service, is called the server side, and this side obviously is the client. Right? The client is the person who is accepting the service. So we can therefore think of the following way in which we provide a service. The server, which is in this case not a piece of hardware but a piece of software, like a web server or an app server generally speaking, is going to set up a kind of a site. So this is where you can obtain service from. It's exactly like a storefront, all right? And the client is somehow made aware of the existence of this service, and therefore is going to initiate a communication or connection with the server, and at that point you can get service. Okay, that's the basic kind of setup, and as you can see, it requires the server to do something different from what the client does. That's why you have basic asymmetry in the client and the server side. Okay, and this is exactly the same for the internet. On the internet, when you go to a web server, the server is sitting there saying, okay, I'm open for all customers, and the client says, I want to connect to this server, and then you connect with the server. Okay, so when you write a networked application, it's necessary for you to divide the application, or at least part of it, into the server side and the client side, where the server is going to set up a well-known address where everybody can get to, and then the client establishes connection with it. And as you can see, this is inherent in the nature of how you provide service, whether it's a peer-to-peer system, whether it's a client server, or whether it's a tree-like structure. In all cases, we need a client side and the server side. Okay, so the way we're going to do this is that the server is going to essentially establish a storefront, if you will, and then the client is going to, so let me draw the semantic things that are going on. So we can draw the client side and the server side like this. So the server is going to establish a storefront, and then it's going to go and listen, right? And the listen is going to be essentially forever. You're going to sit there and just listen and listen and listen until somebody comes, right? Until it's a customer. The client is going to, instead of establishing a storefront, is going to determine the server location. Right? You've got to figure out where the server is, and then you're going to connect. And over here, like so. Right? That's the first thing that's going to happen between the client and server, is that the server has got to be listening, and the client has to knock on the door as a connect. And when that happens, the server is going to do an accept of the connection. And after that, what happens is a connection is established, and both sides can now talk to each other. Even though the client initiated the connection by making the connection over here, both sides can actually talk to each other, and so it's a read and write, and both sides can do read and write. And at the end, either the server or the client says, okay, you're done, close. One of the two or both say close, and then the connection goes away. Right? So this is basically how any service works. You go to a restaurant, the restaurant owner has to set up the storefront, is listening for a customer walks in, you accept the customer, and then they have some exchange, and then either the restaurant owner says go away, you're closing, or the client says I'm done, I'm leaving, and then both ends close, and the transaction is over. Right? So this is how we are going to write network applications. Next level of detail is now going to we're going to figure out, look at how we do these semantic steps. What does it mean to establish a storefront? How do we do listen? How do we do accept? How do we determine server location? How do we connect? How do we do read and write? How do we close? And as you can guess, each of these corresponds to a system call or a library call that's provided by the communications infrastructure. Okay, and so today's lecture is going to be the only lecture like this where we're actually going to look at real code. And this piece of code that we're going to go through is sort of super important. That's why I'm covering it in class, because this is sort of the prototype network application. It's a very, very simple network application, but any network application that you want, including your homework assignments, would be essentially taking this core and then expanding from it. So there's a very, very solid foundation. Once you got this piece of code figured out, you pretty much know how to write a network application for the rest of your life, okay? Which is kind of nice. So it's worth paying attention to. What you learn in this lecture is what you'll probably be asked if you ever take a job interview. They're going to ask you on this, ask you questions about this. And if you ever have to write a network application or use the internet as part of your application, this is what you're going to have to remember. So it's a super important material, practically speaking, if not pedagogically speaking. Okay, so before doing that, I want to talk to you about two data structures. And once you understand the data structures, you'll understand pretty much what's going on. So the two data structures, one is called the socket. Let me get the exact name so that I'm not going to mess it up. So, right, so there's the sock adder. So we should probably call it, okay. Okay, so I'm going to actually, I'm going to talk about three things: the socket table, there's the sock adder, and then there's something called the host end. Okay, right, okay. So the three data structures that kind of encapsulate everything that we're going to do are called the socket table. There's something called the sock adder IN. So this sort of means socket, address, internet, and then the host entity or the host entity. And these names are a bit cryptic, but it doesn't really matter too much. First of all, let me talk about what is meant by socket and then what's meant by socket table. Okay. I'm sure you've all written programs that read and write from files, right? So how many of you have done file I/O in a prior class? So you've all done file I/O, and so you know that to do file I/O you need a handle. You need a identifier, like a file descriptor or some kind of handle to which you can do I/O from, right? You can read and write from that. The equivalent in the network case of a file handle is called a socket. Okay, a socket is something on which you can read and write from, which is exactly what we want to do. We want to connect and we want to read and write from. So these endpoints that you're going to read and write from are called sockets. Okay, so we have two sockets, one on the client side and one on the server side, and these are the sockets. So ultimately what we want to do is to have the client side and the server side both own a socket that they can read and write from, and magically these two sockets are connected, so when you write from here, you read from there, and the other way around, right? So it kind of communicates with each other. Alright, so the set of sockets that are available to a particular client or a server is put in a socket table, okay? So what we actually have is sort of the socket is just the index into the socket table, and the socket table contains all the necessary information about that socket. Who is it talking to, etc. What state is it in? Has it been established? Is it, what's going on with it? All that is in the socket table. And so the socket itself is nothing more than the index into here. So the socket is just it says socket number 1, number 2, number 3, and so on. And it's just a small integer, okay? And so the socket file descriptor is the socket over here, the socket file descriptor, FD, is just an integer basically, okay? It's an int because it's the index into the socket table. So socket FD is like 3 or 5 or 2, and it just points into socket table, which really has all the information over there, okay? The second thing, okay, any questions about socket table, right? And the reason we have more than one socket open is because if you think of a web server, it may have 2,000 open connections. So it'll have a socket table, which has 2,000 entries in it, right? Because you saw the 2,000 connections that are open. The second one is what's called the sock adder IN. This is sort of this stuff over here. What is it that's stored in the socket table corresponding to this socket? So what we really want to know over here, okay, is who are we talking to? Okay, that's basically what we want to know. And so this has got three fields in it. and the socket. So the three fields, one of them is called the address family. And I'll talk about that in a minute. Then there is the IP address, and then there's the port number. Okay. All right. So what is the address family? When sockets invented, which is roughly around 1978, 1979, the idea was that sockets would be used to talk about the internet as well as other networks that existed at that time. Okay, there were many other networks that existed at that time, all of which kind of went away. And I don't want to give you the names, they're not relevant, but at that time, internet was only one of the many networks that were possibly available. And so the idea was that each network could have its own way of naming endpoints. Okay, it could, some could be called using IP addresses, some would use other addresses. So we want, when you say we have an address, we really need to know which network does this address belong to, otherwise it makes no sense, right? And so the address family, today there are only two left. One is called AF INET, address family internet, and the other one is called AF Unix, which means this is sort of what we call a local socket. It's a communication within the server to another. The client and the server are on the same machine. Same computer has both the client and the server, and then we call it AF Unix. We won't really study that very much at all. So let's just assume for now that this address family is basically going to be hard-coded to AF INET because we're not going to use anything else. Okay, pretty much everything's going to be AF INET. The IP address is the address of this endpoint. Okay, so we're going to establish a connection. We're going to have to say which IP address and which port we want to connect to. So obviously we're going to have that over here. What about on the server side? What IP address should we put on the server side? This is basically like a no-op. We don't really want to say anything. We just want to say any address will do. Okay, so either it's the IP of server to connect to, or any means I'm going to accept a connection from anyone. In theory, the server could say I'm going to accept connections only from this source IP address, though it's actually never done. Almost always we say I'll take any customer. It's like saying I'm going to serve only that one customer over there. Why would you want to do that? So we don't usually do that. And then the port number on the client side is which port number are you connecting to. So as you remember, as you may know, web servers on port 80, right? So we have servers sitting on port 80. So on the client side, what we're going to do is to say connect to the port number on the server's port. And on the server side, what you're going to say is listen on this port, listen on port 80, listen on port 50, whatever it is, listen on that port. So this is how we're going to set up the listen. The listen is going to say, oh, I'm going to listen on this port, and the IP address, of course, is your own IP address, and I'm going to accept IP addresses from anyone. Okay. So this is I guess the third thing, and the fourth thing is what's called the host end. The host end is basically a way to describe the destination IP address. Okay, so this is the what is returned by DNS, the domain name server. Okay, so what we're going to do is that we are given a server's name, let's say cs.uwaterloo.ca. Okay, we want to figure out the IP address. Okay, how do we do that? We're going to call the DNS and say, I want to know the IP address of cs.uwaterloo.ca, and what is returned by DNS is this structure called host end, which contains the IP address, but it's in a funny format, and from our purpose, we don't really care what that format is, but as far as we're concerned, this is basically the host address, and then we're going to copy this into here. Okay, the IP address goes into here. Okay. So that's basically the data structures involved in the communication, and then the whole communication then becomes filling up these structures the right way, And then once you fill it up, we can establish the storefront, we can listen, we can accept, and we can do the client side, okay? And so if these structures look a bit complicated, don't worry. As you go through the code, you'll see exactly what's going on. Okay, now we're going to have some, I won't say it's going to be fun. It's going to be a bit dry, but, this is what you get paid for, so. Let's see, what do I do here? Okay, I'm going to start over here, and I'm going to go through the server.c file, and I'm going to actually go through it line by line. I was going to actually write this on the board, but we don't need to because we all have the same thing here, so there's no point. So I'm going to start by kind of really reading through it line by line, and if you have any questions, I'll stop and answer them. So let's start at the top, server.c. So this is a simple server, and this source code is on Piazza, and if you were to take it and run it, it'll work. In C, just like in Java, we have these modules that you kind of import or make part of your program. In C, we use what's called the hash include, and there's a sort of set of standard libraries, in this case what are called header files, .h files that we include, and that's all the GUI up front. stdio, standard IO, standard library, there's some strings that we're using, there's some uni-standard, type, socket. So this set of 1, 2, 3, 4, 7 includes kind of standard, okay, and you can just think of them as being syntactic GUI, and they'll give you the appropriate access to the appropriate data structures and so on. And so I'm not going to go into that very much. It isn't really teaching you much about socket programming. It's just what you need to do in order to get started. The next one is this thing called error. So this error is equivalent of a Java try catch, okay, where we say if we have an error, then p error says print error. P error is this thing, and we basically says print the error message and you get out, exit, okay. So we just want to catch errors. When writing networking code, you have to expect trouble, okay, because so many things can go wrong. You may try to resolve the IP address for a name and there's no IP address, or you may try to connect but the connection network is down. So about half the code actually is error processing, where you say try this, oops, didn't work, get out. And so we have this error because we're constantly getting error. So by and large, the internet works today. That wasn't true when this code was designed and developed. In those days, if the internet worked, it was like a sign of, it would cause a celebration, okay, because there's so many different things that could go wrong, right? From the link could go down, any number of things can go wrong. And so we do a lot of error processing, okay, so that's the error code. So we go into the main. So the main is, well, you know what a main is. It's where we enter into the program itself. And what we have over here is the sockfd. That's the socket fd over here. That's this integer which points into the socket table. We have this thing called new sockfd, and I'll explain that in a moment when we come to it. So we have actually got two socket FDs. We got one over here, the what's called sock, and the other one is the new socket. And then we have this port number, which is what we're going to use to say, okay, I'm establishing a storefront. I'm going to be listening on port number 80, for example. So that's going to be port number over here. That's a port number over here. We have this thing called clylen, socklen, tclylen. Clylen is, it's kind of an archaic thing. It just, we need to kind of have sort of the length of the client that is going to connect to us. And for now, you can ignore that. That's not very important. The next one is the buffer, and that's critical. The buffer is what you're reading and writing to. So when you want to read from the socket on the server side, which is over here, you're going to have to read from the socket and put it somewhere. And that somewhere is buffer, and for that we've chosen an array of size 256 because we're not expecting anything. We're expecting only 256 bytes to come in over here, okay? And that's the buffer over here, okay? Now, some of you may have heard of these things called buffer overrun as a way of doing breaking into servers, right? How many of you have heard of buffer overrun errors, right? So this is exactly how you do buffer overrun errors. Here the buffer is of size 256, okay? So if you give somebody a very large buffer, much larger buffer, right? What would happen is that it would overrun the buffer and then bad things will happen to the server if you don't write it properly. And unfortunately, in the early days when people wrote network code, they didn't write it properly. And so this buffer would get overrun, and that's how you would get attacks on servers, okay? So I won't go into the attacks. You can easily look it up as buffer overrun errors, but this is the buffer that's causing buffer overruns. Then we have we have two addresses over here, the sock adder IN, server adder and client address. So it's the server address and the client address, and these are these data structures over here. So here we're going to describe the server address, and the client address actually is we're going to get who connected to us, right? We need to know who connected to us. That's the client address, and this is the server address. So that's the two sock adder INs, the server address and the client address. And then we have this int n. This n is just basically for us to make sure we aren't going to get buffer overrun errors, okay? And I'll tell you in a minute how we do that with n over here. So those are the variables in this program. What does the structure mean?
It's a variable. It's called.
Oh, a struct is like an object.
Oh.
A struct is like an object. So basically a struct, okay, struct has a name, and then it has field 1, okay, like int, field 1, you know, char, whatever, field 2, etc. And so then that's a structure, it's an object. Right? So it has some elements in it like an object does. So objects in Java came from structures in C. Okay? And so we have these three fields in that structure: address family, IP address, and port number. Okay, so moving along, we have the first thing is make sure you have enough arguments. So in C, by convention, the argument count tells you the first argument is given to the program is the name of the program itself. So if you call this program server, if it says server 24, then server is argument 1, 24 is argument 2, and if you have less than 2 arguments, then you don't have a port number, because you're going to invoke this as server port number. Right? That's the name that's how you're going to invoke it. So you say, hey, I don't have a port, I'm out of luck. So you get out of here. That's that. Then the next part is where we get the first real call, which is sockfd. So we get the socketfd, and we call using the call called socket, okay, which in the socket is basically returning an endpoint to us. Nothing has actually happened. We're establishing the storefront still. So we're calling socket, we're saying, I want an internet socket. I want address family inet, and I want it to be stream. Stream means I want communication to be reliable, so it means I want TCP, okay, and we haven't really talked about stream and datagram very much, but if you remember, I said in the first or second lecture that we have two kinds of APIs over here. One in which we kind of have a circuit, we have a connection end to end, and that's called a stream connection, and so I'll probably write that on over here. So connection, when you have connection oriented communication, so connection oriented is the same as in the internet, same as TCP, the same as sock stream. And if you want datagram, which is not connection oriented, then datagram is the same as UDP, and that would be sock dgram. So what we're telling the system is, give me an endpoint, and this endpoint is going to be something that I want to communicate on using TCP, and it's going to use internet style addresses, okay? And that's the socket call, the 0 at the end, ignore that for now. Okay, so we're saying, give me an endpoint. Remember, it's a server. Server needs an endpoint, so this is the endpoint, we got it. Okay, we haven't had any communication yet, we're just still kind of establishing the storefront here. And the first thing we need is get an endpoint, and we say, I need an endpoint on which I'm going to communicate using TCP. The next is error processing. If sockfd is less than 0, for some reason they can't give you an endpoint, maybe too many endpoints are already in use, you say, okay, I'm out of here, I can't do it, so you have error opening a socket. The next thing we're doing is the B0. What we're doing is, we have this, if you notice, we have the serve adder, which was the sock adder IN, the server address, we want to just be sure that it's 0, okay? Sometimes when you allocate something in the program, it may have some crud left over from the last time the memory was used, okay? It shouldn't happen, but it might, okay? Whenever you get any memory, and it's important like this, it's very important to zero it out, okay? Just clean it out, and that's what we're doing. So B0 is a command that says, fill it with 0 bytes, just clean it out, and that's B0 over here. And we're saying the size of the structure is size of server address, that's how many bytes you want to fill, and the pointer is ampersand server address, this is the address, and then this many bytes, just wipe it out, fill it with zeros, okay? Again, just being careful. Okay, I'm going to go to the other place over here. So we have memory over here. This is your RAM, and somewhere in memory is this servadder. Okay, and the ampersand servadder is a pointer to that. All right, and we're saying treat it like a character pointer. Okay, pretend as if it's a character, and then go basically zero it out with B0. That's what we're saying over here. Okay. Any questions? Yes.
So why do we need to force it to be a character?
Oh, I see. Because the thing is, B0, the function called B0 takes character pointer. Oh. It's a function. It's a byte 0. B stands for bytes. I'm going to zero out bytes, one character at a time, one byte at a time. So I need bytes. Okay. It's let me put it like this. This is how the things are done in C. Okay, if we want to zero out bytes, we just say we zero out bytes. We don't really care what the underlying structure is. We're going to wipe it out clean anyway, right? So that's what we're doing over here. So this length is size of. That's the size of the servadder. That's the size of that structure. Is obviously size of servadder. That's, let's say size of servadder is 20 bytes. Then we'll say, okay, for this pointer onwards, for the next 20 bytes, put zeros in it. So we're cleaning it out. Okay, that's how we clean stuff. Okay, and I think Python doesn't do this either. I think Python you get a clean, when you do something, you get a clean. Any language which has new, gives you clean stuff, but C doesn't actually. It's supposed to, but not always. Okay, all right. So next we have this thing which says port no. Okay, I'm going to clear this so I can. So the next one says a port number, which is the idea over here. So A to I argv1. So let's look at this a little bit. Port no equals A to I. Oops. Argv. So there's a lot of stuff hidden in this little thing, but it's actually pretty straightforward. So first let's look at argv1. So the parameters that are passed into the program are called the argument vector. Okay? And the argument vector looks like this. So your argv0 is the name of the program by convention. It's a string. Argument 1 equals first string passed in, and then argv2 equals second string that's passed in, and so on. So for example, if I invoke this as server, okay, A, B, C, then argv1 will be A, argv2 will be BC. And there'll be the string A and the string BC, okay? So this would become A, and this will be the string BC. So automatically going to be of type string, okay? So this is a string, okay? But remember, we want a number. Okay, we want the port number, like 20 or 84 or 2000, right? So A to I stands for ASCII to integer. And so it's taking that string, like, the string, let's say, in this case, if I say server, and I give it 2400, then I'm going to get this string to be the string 2400. And then this is going to be 2400. And this is going to be 2400, the integer, because A to I converts the string into integer. Okay? And that's A to I for you. Okay, so that's why we need it. Now the argument count, by the way, is argc. So argc is going to be 2 over here, because the first argument, second argument, if I have that, then argc will be 3 and so on. Right? Because there are 3 arguments, name itself, and then the first 2 arguments. We were at this line that says port no equals A to I argv1, and what we've done now is simply to get the port number from the argument that was passed in, let's say 2400, and that's the port number that you can listen to. So at this point I should add that in most computing systems, though not all, any port numbers below 1024 are considered to be privileged ports or special ports. So if you try to if you try to establish a storefront on a port number below 1024, you have to be a special user, privileged user. And so certainly on our Unix systems that you're going to be doing your homework assignments on, we have that. So don't try to connect, don't try to establish a port number on the server side below 1024. So use any number higher than that, between 1024 and 2 to the power 16, 65,535. Those numbers are all okay. Anything beyond that is not good. All right, so we're now going to start filling up the sock adder IN structure. Okay, that's the next 3 lines. Serve adder.assign family, address, and port. Do you see those 3 lines? Everybody see those 3 lines over here? Serve adder.assign family, adder, and port. So the details of this structure are not super critical, but I'm just going to tell you that the family is AF init. We said that. The SIN adder.sadder, this is a sub field, but it's not important that it's a subfield. It just basically says any. So the specific thing is this: capitals IN adder any means it's a predefined type in the header file. It says I'll accept anybody. Okay, that's what we're doing in the next line. And the last line, serve adder.sign port. Okay. SIN port, it's not SIN, it means S stands for socket, IN is internet. So internet socket port is this funny thing called H2NS port node. So we have H2NS port node. So I'm going to explain that in a minute. So let's look at that. H2NS port node. Do you see that? So the reason for this particular construct is the following. When we have a byte in memory, right, a byte is 8 bits, then we can do, so that's 8 bits, that's 1 byte. Okay, that's easy. Okay, that's easy to represent. Everybody represents it the same thing. This is the least significant bit, and this is the most significant bit. Okay, so most significant meaning the highest order bits. This is 2 to the power 7. This is 2 to the power 0. Okay, so that's how we do MSB and LSB. Okay, so right now if we have 2 bytes, then we have what's called a short. Short is 2 bytes, so we have 1 byte like this and the other byte like this. And so it turns out there are 2 different ways of representing this. So here we always have MSB and LSB over here inside each byte. But it turns out that there are 2 ways of representing this, and we just call them 1, 2, 2, 1. So we kind of swap them around. Okay. That's the way it's done. So some computers represent it in this way, some represent it in this way, and there's some they're very abstract arguments why one is better than the other, and it's not even worth arguing. And these are called big endian and little endian approaches. But anyway, it doesn't really matter what they are. We want to make sure that when we send a shot into the system, the other side is going to get the shot as well. It's not going to get something that's swapped around, right? We want to send, if I say port number 2400, I don't want the network to interpret it as port number something else because the bytes got swapped around, okay? So what we have is what's called network order. This is called the network order, network byte order. And this is called the host byte order. And what this is doing is it's converting the host byte order to network byte order for a short. Okay, and so you take the port number, which is an integer, which is actually a short, which is 2 bytes, or what we call a short, and you're converting a short from host order to network order, and that's what you're filling into this port number over here, because we don't want the network to be confused. We say the network order is this, no matter what the host is, it must give it in that format, and we give it in that format over here, okay? And that's what the H2NS is doing. Once we do this, the next call is, the important call, that's the actual establish the storefront. So that's being done using the bind call. So we first got the socket. That gives us the endpoint. Now we do the bind. And the bind call, if you look at it, is basically saying, okay, I have the sock FD, that's the pointer over here, and I want to fill in those fields over here, and I do that using the bind call by giving it the server address, okay, which has all these fields filled in. Okay, I have all the fields filled in, I just fill them in. I'm going to now fill in these fields and stick it in, and that's done using the bind call over here. So you do the socket call with the bind call. At this point, this socket on the server side is listening for any incoming IP address on the internet on the port number, and the port number came from the argument through A2I and then H2NS. Okay, those are the two steps. Okay, so remember that what we're trying to do is to establish our storefront. So first you need an endpoint. The endpoint is an entry in the socket table, right? So first we want to get a sort of empty entry over here. We do that using the socket call. Socket call returns to us a socket FD, let's say 5. So these guys are used up, I get a new one. Let's say that's what's going to return to me. Okay, that's a socket call. Okay? That's a sock FD equals socket AFINet sock stream 0. Okay, then after that, we are getting we're clearing out the serve adder, which is the B0. We're finding out the port number, and then we're filling in the serve adder with the addresses, with the information. We want AFINet, we want INet or any, and then we want to put in the port number as being what we got from the command line argument, H2NS port no. Okay? And then bind says, okay, all this information, just stick it in here. This is what the bind call does. Because these three things have got to go over here. And that's binding it, it's putting it on. That's like putting up a nameplate that says, this is my tattoo parlor, right? This is I'm going to accept anybody, who's coming on the internet and who's on this port. Okay, that's what I'm saying over here. Okay, so the bind sets it up, and then at this point we're going to go and listen. Okay, that's what we're doing with the listen call. It says, okay, I have this set up, I want to go listen to socket ID 4, right? That's what we're going to do. And the 5 is just ignore that for now. That's sort of, it's not important right now. That has to do with a very large server and many things are coming in. But for now, just ignore the 5, and we're listening on this 4 over here. And now what's happening is that we're going to be blocked on the listen. We're going to sit here and listen and listen and listen. And now when you go to the client side, you'll find they're going to do a connect. And that's when we're going to come out of the listen. So listen is a blocking call. We're just kind of waiting. And then the next one, the CLILEN, remember the CLILEN is this archaic thing, we don't really need it, so ignore that. What happens next is the interesting part, where we say new sock FD equals accept sock FD, CLI-adder, CLILEN. What we're doing over here is that when we accept, we get a new socket address, we get a new entry over here, like 5, okay? This is the socket that we are listening on. And every time we accept, we get something new over here, okay? And the reason is like this. I have a customer coming to my tattoo parlor. While I'm tattooing them, somebody else may show up, right? What do? Well, they're going to sit there, basically, waiting at the door until I accept them, right? But what I would like to have is something like a waiting room, right? I want to have somebody come in, and while I'm doing the work, this is sitting there, and then I can keep accepting people, okay? So I want to sort of be able to listen always on the port number, which is a well-known port number, but as each customer comes in, I'm going to assign them a different port number and a different socket information over here, and so each customer would have its own separate socket thing. So I want to kind of hand off and create new temporary sockets, if you will, new temporary entries in the socket table corresponding to each connection. So I'm always listening on port 80, but as people get accepted, they're going to be handed off to port, let's say 32,000 or port 74,000, port 64,000, whatever. Right. So people, I have tattoo parlor, multiple sort of tattooing, I have people working for me, so I'm always listening, but they say, okay, go to room 1, you go to room 2, you go to room 3. I'm always listening on the front door. That's my listening. And then each connection I accept results in a new connection in the table over here. Okay, and that's what's going on over here. So if you look, you see carefully, I get this thing called new sock FD, it's a new socket, and I'm accepting on the sock FD, on this one over here, And then the next two are basically saying, tell me who connected. The client adder is the client address, which looks just like the server address. So it will tell you what address, which IP it came from, and which port number it connected to. Okay, but we don't really care. In this particular example, we don't really care, but you can care. That's how Apache knows where you connected from. So just a moment, I'll come to you. If you remember the homework assignment, if you see the homework assignment, with this thing, it says you are coming from so-and-so IP address, right? You are coming from Kitchener. You are coming from this browser. How does it know where you came from? It came from the CliAdder parameter over here. Okay, so at this point we're pretty much done because we got the new sock FD. Now what we're going to do in the next line, B0, is we're going to empty out clear out the buffer. Okay, the buffer is already character, so I don't need to cast it. I just say B0 buffer is 256 bytes, just zap it. And then we just read on the new sock FD. So this new sock FD we got over here is the one that we're going to read and write on from the server side. Okay, so we just say read. So whatever was sent by the client is going to be read over here. Okay, and now there's a gotcha over here. And the gotcha is that if the client writes, let's say 20 bytes, the server, when it does a read, may not get 20 bytes. It may get 5, it may get 10, it may get up to 20 bytes, but we don't know how many bytes. Okay, and the reason is because it may be necessary for the client side, if it's a very slow connection or if there's a lot of what's called network congestion, to send fewer bytes than what it wanted. So you may say send 20,000 bytes, but you may not be able to send 20,000 bytes. You may only send 200 bytes or 400 bytes. So when you do this read over here, n equals read, that n tells you how many bytes you actually got. Okay, it's how many bytes you actually got, and the 255 at the end, that one says read up to 255 bytes. In the bad buggy code, what happened was that people didn't put the value of 255, they put a value of 0. That means read whatever is there. Okay, and that's what caused buffer overrun, because somebody sent more than 255, that would cause this read system call to happily overwrite the buffers. Okay, by limiting to 255 over here, putting the 255, we make sure we don't get buffer overrun errors, and that n tells us how many bytes we actually got. Okay, now that we read it, we got the bytes. We actually had network communication happen. The client sent some bytes and the host other side got it. We managed to achieve network communication from anywhere to anywhere on the internet. You could be sitting in Antarctica or on Mars. Once you get the read, you got the bytes from Mars, which is fantastic. Okay, the feeling you have when you write this code and run it is quite awesome. The client side, I'll go through it pretty fast because actually it's pretty straightforward. If you start at the top, you have the same includes. The structures that you have over here are almost all the same, except we have this new structure, this host end structure. Okay, and I'll come to that in a minute. Everything else is the same. Okay? So if you go down, the port number equals A2I argv2. Here we're saying that we're going to have the arguments as client, the name of the server, and the server port number. So you say client, linux.student.cs.uwaterloo.ca, port number 34,000. That port number is the third argument, so it's argv2. And then what we're doing is we're establishing the client side kind of socket. So we do the socket, same thing, we got the socket endpoint, and we're calling that sock FD. Remember, this client side we have a socket table as well, there's a socket descriptor. This gives us a small integer like 3 or 5 or 7, which is the socket FD. Okay, then after that, the only difference between client and server really, the main difference is over here we see server equals get host by name argv1. Does everybody see that? This is how we get into DNS. So we're getting into DNS and we're saying, hey DNS, I'm giving you this name, cs.uwaterloo.ca. Tell me the server's IP address. And so we say get host by name. So give me the host's IP address. That's a getting the host by name and giving it the name. Okay, and that returns to you the server, which is a host end, right? The host end, which is what is returned by DNS, as I said earlier. Okay, and then what we do at this point is we zero out the server address. We set the server address to be inet, the address family to be inet, and this b copy over here, where you're copying from the server pointer hadder to sinadder.sadder. This copy is essentially copying the IP address into the socket. Okay, So that piece of code over there is not very nice, but what it's really doing is it's copying what was returned by DNS, the host ent field, into the serve addr field, and then the port is being set. Again, H2NS is being done. The next line, serve addr sign port, is H2NS port number. It's setting the port number using H2NS as before. And then finally, we're doing the connect. What we're saying on connect is connect on this socket that I got using the server whose address family and IP address and port number I just set up. Okay, and that's it. Connect. So at this point the connection is established from here to here. Once you do that, that sock FD can be used for reading and writing. And so we see over here, zeroing out the buffer. The fgetS from stdin means read from screen. Read from keyboard, I'm sorry. Standard in is keyboard, read from keyboard, and then write to the socket, and we're basically done. Okay, so the last few bits are pretty straightforward. So on the client side, what we're really doing is we are setting up we're figuring out the IP address in the host tent data structure, and then we are setting up the entry, but we're not using bind for it. We're just using connect, and connect takes the entry over here, puts it in the table for you. It's part of the connect, and at this point you have a sock FD that you can read and write on, and you'll see what's happening. I would encourage you to log into your Linux account and run the client and server side, run them both, connect to them, see what happens, modify the code. It will be really instructive. So this is all I'm going to talk about for the socket programming, and on next 2 weeks Andy will be talking about TCP. So transport layer. I'm going to go straight into transport layer from now on.